Hello, welcome to this webinar on seismic data processing using InSite seismic processor. My name is Juan Reyes Montes. I'm a geophysicist and consultant at Itasca, UK, and I will guide you through the main steps in seismic processing and how each of these steps is done using our tool, which is InSite seismic processor. So, what do we mean when we talk about applied seismology? Well, it is simply the application of the technologies, the techniques, and the methods of earthquake monitoring for the imaging and interpretation of the impact of any engineering processes on the surrounding environment. By using the methodology of seismicity, of traditional earthquake seismicity, we can obtain information on the condition of the rock mass, or in fact, any brittle material, any brittle structure, that it's subject to changes of stress imposed by different types of human intervention. It can be mining, it can be hydraulic fracturing. Lately, instrumentation has advanced a lot, making it more widely available and easier to have instrumentation that applies to all the different applications that cover the expected spectrum for the signals in the different context. Not only that, but especially processing power from normal standard computers have improved so that managing large sets of data now it's easier, so we can work with dense networks of arrays and obtain a much better picture of the fracturing process. And we've heard the term of microseismicity. It's just a small earthquake. We've heard about the term of acoustic emission. Exactly, we're talking about the same phenomenon. But why is it important? Well, mostly because it is the only or the first information that we have about what's happening inside a rock mass in real time, as we are changing the stress conditions around it due to any different operations, any different engineering operation. And as such, it's applied in many fields. It's routinely applied in mining, for the monitoring of geothermal stimulation, for the monitoring of geological repositories for the storage of hazardous waste or gas, in the oil and gas industry, as well, stimulation of reservoirs has become has extended to many new reservoirs, and in general in any civil engineering application where we are dealing with either rock masses or brittle structures such as concrete pillars, etc. Okay, so what's InSite? So InSite is a Windows platform, a Windows software developed by Itasca over the last 20 years that integrates all the steps in seismic monitoring. It integrates the acquisition of data, the management of this data, processing, the analysis, and the interpretation of our observations. As I said before, it's been developed over the past 20 years, incorporating more tools every time based on our own internal research and development, and especially through collaboration with our clients that work in the most diverse fields and scales. So our clients work from rock testing in laboratory, detecting acoustic emissions, trying to image fractures in rock samples, up to monitoring of regional earthquakes, regional seismicity that's either induced or natural. And our latest version now, it's 3.16.1, and was released last month in March 2019. Okay, so what are the steps in dealing, in monitoring seismically any rock mass or any structure? Well, here is a quite comprehensive workflow that hopefully covers all the aspects of this monitoring process in job. The first step, we can see here, is of course is a feasibility study, designing and positioning our tools where they provide a good coverage that meets the objectives of our monitoring project. And as in everything, we need to set up our projects. And this is the first step that we're gonna see how it's done within InSite. Slide. So this is a view of some of the visualizers in InSite, but the main steps that we need to take when we start working on our seismic project is having some instruments. Instruments acquire waveforms, and each of these waveforms need to be linked to an instrument. So that's the essential step that any project should have. We need to import our traces, our waveforms, and this is done through the addition of receivers, sensors. More optional information, of course, if we want to process those, is adding some geological or engineering structures for interpretation, adding velocity structure into our model, if we want to locate the events, etc. So there are several ways we can do that, and I think it's better if we have a look at the program itself. So this is the first window that we see in InSite when we open it. It's a window that looks very much like Windows Explorer, where we have, because we don't have anything at the moment, we haven't started our project, it is all blank. But we will see as our project develops and we get data, we will have a pane that shows this panel that shows folders where our data is stored, our events are stored. And here we will have a list of events as we get them, or triggers as we get them. But first step that we need to configure our project is, as with any Windows or any software, in fact, we can save our project as a standard file, PCF file, and we need to add tools. So one way to do that is manually. We just have this dialog here where we can add a new instrument. Instrument can be uniaxial, that's the default. So we have here one axis with a certain position, default is 000. We don't need to know this at the beginning of our project. This can be updated later once we know the information. The crucial information is how many instruments and whether they are uniaxial, triaxial, or even quadriaxial. That's the essential information we need to know, the number of channels, the number of receivers that we're going to use. So yeah, we can add that manually. If it's triaxial, as it's the case in typical case in downhole monitoring, we can add channels. If we know the response of our instruments, we can input that here in this window. So yeah, we add the channel. We don't need to do that now. Okay. Click OK, and we have one instrument. And so on. We can keep adding that. If we want to use an easy, or if we have more information, basically, and we want to enter that, we have an easier interface. It's called Setup, Frag Manager. That it's, at the moment, it's ideal, it's customized for adding downhole tools into our project and all the information associated with them. So, because there are downhole tools, the first piece of information that we need to add is wells. Where are our wells? What's the track of these wells? So we can add this here. Let's import a monitoring well. So we can import that from a text file, a file that contains northing and easting for the track of our well. Can be vertical, can be deviated, can be in any configuration. So that's what. And I've already prepared a text file, simple file, that contains the track for our well. Because it's flexible, we need to tell the software what information is under each of the headers in my file. I made it very easy, so I put the right labels in each of the columns of my file. If you don't have that, it's fine. All that the software needs to know is identify what type of information is in each of the columns. I have northing, easting, measure depth, and true vertical depth. You don't need all of this. You need to have a pair of this, well, 3 of these, one type of depth, and either northing and easting or azimuth and inclination. So once I have that, I know my well, where it is stored, I can just add it. If it's a vertical well and I don't have the right track for it, I can, with another file, we can add it as this. We just position the head, tell the software how deep it is, how deep it goes, and it will be written. Okay, so we have this well, and we can add a treatment well. So treatment survey, and because it's following the same pattern as before, the software has identified that it's fine. I know how it works. So here we have the 2 wells, and we can see here in the input that the columns have been read correctly and the trajectory has been input into the software. Next step here, we can easily deploy or enter our tools there. So we can do that again through a text file that contains their position, or we can add it. We need to know everything, so I call it test. I will say we have 10 tools with the top tool positioned at, let's say, 1,000 feet down with a spacing of 30 feet. I'm telling the software that, it's triaxial, it has 3 channels. Each tool has 3 channels, and this is the relative orientation of these 3 channels. Z pointing up and X orthogonal to Y, 90 degrees anti-clockwise. Excuse me. We can enter here the response. As I said previously, we don't need to have all the full information at each stage. All we need to know is how many instruments and how many channels are we recording on. Okay. So here it is. I've input my tools into it. We can enter sonic logs if we have them. We can enter more objects. But it's the same process. It's a text file that contains all this information. Okay, so I will add one stage because we need to have one stage at least. Yep. Okay. So, well, software is telling me I haven't completed everything because I have not oriented my tools. So yeah, of course, because we're only setting up our project. So you can see I will exit. I don't know any further information at the moment. All I need to know, if we go to the 3D scene, the visualizer, is that my tools, my wells are here. You can see the wells. Well, by mistake, I put one over the other because I said that both were sharing the same wellhead. And my instruments, if I zoom in, my instruments should be, I'm gonna navigate through here. Yeah, I can see them. Zoom in a little further. Our tools are positioned there. Okay. Right, so let's go to the next step, which in fact should be the previous step, but InSite needs this configuration to start with. But we're going back one step, which is a feasibility study. That it's optimizing the position of our tools. If we have the flexibility to position our tools, our stations, in different positions around our volume, our objective, then InSite has the tools to perform an optimization of which position for these tools will give us the optimal coverage for our objectives. And it's basically the software, what it does, it runs a simulation. You enter a proposed position for the tools, and the software will tell you how well will they perform. And how well will they perform it's evaluated through a series of simulations. One is the calculating what's the distribution of the threshold magnitude, that is the sensitivity. So how sensitive it is in the different points of our volume. So ideally, it should have the highest sensitivity at the point of interest and as uniform as possible. We also want to make sure that our location algorithm will perform well, will converge to a unique solution. So this is done through looking into the misfit space. It basically plots what will be the topography of the search space that the location algorithm will have to work with. In scenarios typical of mining or civil engineering, we have normally we have voids, we have tunnels, we have many structures that might might obscure the propagation of our ray paths. And this is studied through the shadow space. We can enter our structures into the software, and the software will tell us how many stations are, how many sensors are in line of sight from each point in the space. Basically, how many of them are not blocked by any of these structures. And also has the tool to kind of estimate, simulate what would be the expected location error. And it's just done running a Monte Carlo simulation. That it's running the process of locating a theoretical event, altering the main variables in the location of our event, which are the travel times and the velocity model, altering them randomly, and will give us what is the estimated error we'll get in our location. Okay, and we also have tools to generate what will be the expected pattern of arrival for our waveforms, our traces. Okay, so let's go back to the software. Let's have a look at. Yeah. So we have here a project different from the previous one that we work with. This case is the monitoring of a gallery. This is for a graduate repository. It's an experimental gallery that was going to be drilled in this area. Here we have the CAD drawing of the final excavation, and it's surrounded by a series of stations. We have 12 stations that are surrounding the volume of where the tunnel will be excavated. So ideally, we want to have a good coverage of the estimated excavation damage zone, which is where most of our events will be induced. So this tool is called array analysis, and it will allow us to perform the simulations I was talking about before. We have a number of variables to enter here. These are display variables, which is the volume where we want to calculate the performance of our array. We can have a plot in any of these three planes. Let's do initially this vertical plane, north-down plane, resolution of that plane that we want to display, and where we want to position that. And of course, we need to define a folder where we want to store these results. We also need to enter some properties for our location algorithm, because it's going to use locations to perform the simulation. So we want to see how our algorithm will perform with the current configuration. And this is the suite of simulations that we have. I'm going to just run a few of them, the ones that are fastest. So let's have a look at our magnitude sensitivity. And here, all we need to input is basically what's roughly the properties of our rock mass. That's given by the density and the Q factor, attenuation that we are expecting to have. Some parameters characterizing our tools, and what is the minimum number of peaks that we want to have for one event to be properly detected. I'm being quite conservative here, asking it that it has to be detected by a minimum of 6 stations. So let's run it. And it should be pretty fast. Yeah. Let's close and have a look at it. Close. And this is the result. So what it's done, it's for each point in the plane that I have asked the software to model, for each point in this plane, what is the threshold magnitude for an event to be detected. The values, we can have a look at them here in the color scale. They range from -4 to -3. They're very, very small events, so it's a highly sensitive array. But the important information that we have is the highest sensitivity is around the area where our tunnel is going to be excavated. So we have the highest sensitivity there, which is correct. That's good. And it's, well, almost homogeneous. It's ranging between -4.3 and -4.1, which, yeah, it's good for the objectives that we have here. Okay, I'm going to hide it. So we're going to run the second simulation, or the next simulation, with misfit space. And here I will need to define is position an event, a theoretical event. I have already entered that. I put it on the roof of our gallery. And what it will do is calculate the residual space for it. It's a pretty fast simulation. So what is the ideal result is basically what we have here. I'm going to show the color scale. We expect to have a minimum misfit around the position of our event. And yeah, we got it. Basically, we have a well-defined minimum. There are no potential local minima in other areas. And this minimum is the difference in between the theoretical travel times and the observed travel times. Of course, in this case, it's all a theoretical event, but that's what the location algorithm will be working with. We're trying to find the position that minimizes the difference in between theoretical and observed travel times. If this position is well defined, yeah, we expect our algorithm to converge, have a single robust solution. If this minimum was wide, the solution would not be very robust and we might have different potential solutions, and we might need to fine-tune our location algorithm, fine-tune our mislead. If we had minimized other points, then it will not only be not robust, it will not be stable, and it might be trapped in a wrong solution. So it's good. That's what we expect to have. Expect to have a good performance. I'm gonna hide it, and I'm just gonna run a final simulation, which is the Monte Carlo simulation, which what it does is alter the arrival times, in this case by 1 millisecond. It's a bit too much for this context. I will bring it down slightly. And alter what's the uncertainty in the velocity model and the uncertainty in the P velocity and the S-wave velocity. And it's going to perform it 250 times. In this case, we can go as high as we want to go. And it basically locates events that have altered their arrival times and have altered the velocity model. And they will be displayed here. Yeah. So basically what we expect to have is that this is our uncertainty for an event that's located at the center of this. So not too bad, basically because we're dealing here with a good array with very good signals. We know this afterwards because we've worked in this project. So yeah, this is a good estimate of what would be the uncertainty in our location. Okay, so let's go to the next step. Well, now we have configured everything. We are sure that our array will perform correctly. So the next logical step is getting data in. So InSite is ready to work with already processed data that has been triggered, that traces events have been identified and are basically not pre-processed or not processed, fed into InSite, or harvest events, that is working with continuous streams, continuous data that is coming from the sensors, and detecting those events. And that's what's tricky, how it involves more processes into it. But basically what it tries to do is detect when our stream meets a certain criteria, normally based on amplitude, that will tell us that there is an arrival. It's an amplitude that is above the normal background noise. So anything that goes above that noise should be a signal. If that's done across different instruments and there's some coherence, that means that it's a signal coming from or potentially coming from an event, not a spurious spike in one of the instruments. And it's done very simply. We have here two windows that scan the whole trace, looking for these triggers. We have a front window that's got the signal and a back window that's in the noise. So when the amplitude in the front, or whatever value we estimate, and we'll talk about that later, in the front exceeds the value at the back, that means we have an arrival. That can be identified as an arrival. And we also need to consider that arrival is not only achieved in one station, but coherently across different stations. So let's have a look at InSite. Let's open the software again. Let's have a look at the tool that works with the streams. I'm going to go back one step out of this. If our events have already been identified and are recorded, we can directly import them. It's as we import anything in Windows. We need to tell the software where these files are stored and where we want to store the processed waveforms. InSite works with two types of files. One file that contains the project, basically all the configuration and all the results, and then separate files for each of the traces. And well, basically InSite can import over 30 different formats. Most of the standard formats are in there, some proprietary formats, and yeah, it's very easy. We're always happy to add new waveform formats into it. So yeah, so this is the case where we are working with already trigger identified events. Let's have a look at what if we are working with raw data, continuous stream of raw data. That tool is called the InSite Leach. It's here, triggering, called by triggering. This is the InSite Leach, and it's as everything, as import of data, we need to tell the software where our raw data is stored, where do we want to store our identified events, the traces for our identified events, and where do we want to store the backup. InSite creates a backup file, because this process can be quite intensive, it might take a lot of resources, and there's always a potential for crashing. And so to avoid that, we always have a backup. And there are different ways to detect our events. If we're dealing with very easy data, not noisy at all, and we know anything over a certain amplitude is a trigger, we can just work simply with that. And it's pure, just define what will be the threshold amplitude that we need to exceed. Most typically, it's not so clear that it's a fixed amplitude that will define a trigger, so then we work with the double window that I mentioned before. That's the picking algorithm. We define here the size of our signal window, the front window, and the noise window, the back window. Always, yeah, the back window should be larger than the front, because we need to make sure that we are properly scanning and characterizing our noise. And then we also need to define, okay, what's a coherent arrival? In our case, we say that, yeah, a minimum of 3 instruments, not separated more than 200 sample points in between them, should have arrivals not separated more than 200 sample points in between them. So that would define a coherent event. What defines a coherent event depends on the context, depends on our array, and depends on how far we are from our potential source, etc. So there are many considerations to take into account. So I'm going to run it just to show an example. I will say start leaching data. So the first thing that the software does is look at the raw files. It says I found, in this case, 100 raw files. You want, I know here there's a bit of feedback you can have, where InSite is telling you what file is it looking at, if it has detected a trigger, quite a few of them. So yeah, so the process goes on until soon it will reach a point where it says there are no new files. I've been through all of them. InSite is basically optimized, or it's written for working in real time. So that's why we keep it open. We can keep it looking for new files all the time. If we have pre-processed, pre-recorded data, then yeah, we know we've reached the end, so we can close it. We can stop it, and we can have a look. And normally it's good to have a good quick check to see if we have trigger or noise, or if our events look real. And our events look reasonably real, so we don't need to change much our trigger parameters. If anything, I will probably go and make it a bit more sensitive until it brings some very, very small events into our set. So far, yeah, it looks good. Okay, so now we have traces. What's next? Let's go back to our presentation. Picking. We need to identify our arrivals. Normally in seismology, we work with arrivals. So we identify our event through the arrival of typically a P wave and an S wave after it. Could be many more, and there are many more phases, of course. We might not see one of them. Sometimes P wave is highly attenuated, but we need to detect it. How is it done in InSite? It's very similar to what we've done now with the leach, only that it's done trace by trace. It's looking, in this case, at a single trace through this double window, and yeah, set a criteria that will tell us that there is a signal arriving at that point. The signal is above the noise for some reason. It could be, or for some criteria, sorry, it could be amplitude, but InSite has a flexibility to detect, also take into account other variables such as changes in our frequency content, changes in polarization, etc. And this can be customized for P wave, for S wave, and can be customized for each single receiver. Each receiver might behave differently, might have a different response. So we might need to customize it for each of our receivers. And yeah, let's go back to the software. So it should be here. So we're going back to the downhole example where we triggered before. So we have our array, down the monitoring well. If we go back to our data visualizer, we've seen that it triggers, not yet events because we haven't done anything with them, but there are triggers there. They've been populated. I forgot to mention in the previous step that as I mentioned before, this is almost like it behaves almost like a Windows Explorer, where we have folders. We can create folders, we can add the core components, so we add components here, these are folders, and these are like files which we can enable or disable. If they are disabled, they're still there, we're not deleting them, but they will not be looked into. They will not be processed, and they will not be dealing with them. We can create copies, we can move them to a different folder, etc. We can work with them as we work with any file in Windows. So let's have a look at waveforms. So if we call the waveform in one of these events, there we go. Here we have the arrivals. They're pretty reasonable, and different ways to detect our event. This one is an easy one, so I can see everything. I can do that manually. So if you see this, yeah, add P wave arrival. It's quite clear. If we pick the wrong position, we can move it. Yeah, right here, and so on. If we're not happy with that, we can cancel and start over again. But we can also do it automatically. Normally what we do is we go to one of them, do it manually, see how it behaves, and then do it automatically. And that's set up here in auto picking, the properties for our picking. And we can see there are different methods to identify this arrival. You can identify it based on the RMS amplitude, that it's taking into account the RMS of the traces, all the traces in one instrument. You can use the envelope over this RMS, or we can use the Akaike information criteria, that it's basically, or simply, to summarize it, is a autocorrelation. It will try and characterize. We can use different bits of information that we have to characterize our noise and our signal, and this way it will try to identify the signal. Okay, so a standard one is, yeah, looking at envelope or RMS. They're very similar, but you can see here it works very much like the leach, like the trigger that we worked before. Front window, back window, any threshold. Same thing for the S wave. We have here, because by default the software will try and find first the P wave and then the S wave after it. That's a standard behavior. But there are many cases where our P wave is too weak, so we might want to start with the S wave first and then go back and pick the P wave from it. So yeah, many options here, basically to customize, to adapt our search for the scenario that we are dealing with. This is an easy one, so yeah, we can auto, and that's it. And we can further automate it by call the auto processor. You don't have to go event by event, so we call the auto processor. We're not ready to locate yet, so yeah, let's locate. Sorry, let's pick. Let's pick our event. If we want to pick amplitudes, yeah, we can do that. Anyway, so that pretty fast process, so it's going through all of the events, and now they should all be picked. No changes because we haven't processed anything yet, so there's no information on where our event locates. But can go back and see that, yeah, picks a research channel, grab it off. We can optimize that. And I'm going to show you the last tool that can be useful here, and that it's I've set randomly, not randomly, and I had some information before to set what's the size of our windows, what's the threshold I should be using. But we can teach InSite, we can ask InSite to tell us what is the optimal configuration. So how do we do that? Well, basically, we go and manually pick our event, say, yeah, this is our arrival. So if we call the tool called Educator, basically tells us what are the conditions of the signal and the noise around the position. I've put my pick, and it will recommend a size for the front and the back window. Yeah. See here, best fit. And we can say, yeah, well, update, yeah, I want to update actually my processing properties to these ones that you've told me, and I will reprocess everything. Right, so we've seen this step, we've picked our arrivals, and then we move on to the next step, which is crucial one, or the most important one, which is we want to locate our events. Events are characterized by, well, many parameters, but the main one, the most important one, is where does it locate? So how is it done? Basically, or very simply, most of the algorithms that work in InSite to match observations that we have at other times, basically, observations with theoretical values. Theoretical values are calculated using a velocity model. This velocity model can be any of these that I'm showing here, can be a very simple homogeneous isotropic. We can have some degree of anisotropy, but it's a constant anisotropy for the whole volume, or we can introduce more complex models such as layers with anisotropy, or complex models, not only layers. And finally, we can work with multiple velocity models because basically our velocity changes, or the properties of a rock mass changes during the monitoring because we are either fracturing them or doing some engineering operations around it. So we might work with several velocity models, and this is called the time-dependent models. So how is this comparison done? That's why it's called the inversion algorithm. Once we have the theoretical behavior, we have the observations, then there are different algorithms to search for the ideal for the best fit position. So with homogeneous media, we have these two tools. They only work in this media, Geiger, only for isotropic, or simplex for isotropic VTI. Simplex is a search method, and Geiger basically is just the inversion, the solution, basically, the solution of the travel time equations. If we want to work with more complex media, we have to use one of these tools, the collapsing grid search or the source scan. What's the collapsing grid search? It's very simply, it's an exhaustive search in a volume that it's being gridded. It's collapsing because just to make it more efficient, because it starts with an initial very coarse grid, just to save time, to make it more efficient. When it finds, when it locates the first best fit around that grid, it focuses around it with a finer grid. And at the end, yeah, it will produce what will be the misfit around it. Source scan is slightly different because, well, grid search basically tries to match arrival times. Source scan is a bit more elaborate because it finds the best fit for an objective function. That function can be anything. And in fact, it doesn't need peaks around it. It tries to focus, it tries to optimize what would be the position in our volume, the location in our volume, that optimizes, that may give us a maximum of this objective function. And the objective function can be the energy in our arrivals, it can be polarization, it can be any piece of information that it's useful. But basically, yeah, the main advantage is that in very bad data sets where we cannot easily identify arrivals, it gives us an extra hope, an extra tool to work with them. So, yep, here is in text what I have already said. But yeah, we have a signal window, we have noise windows, they move around, they scan the whole trace, and they try and find what is the point in the space that it's optimizing whatever we ask the software to look for, to use as an objective function. And the search is accelerated using the Gaussian particle swarm optimization. So let's go back to the software. We have different examples here. So I'm going to show a handful of three of them. So first example is going back to the tunnel that we saw before. The 3D visualizer. Yep, we have this tunnel here. And now we have a series of events that, if we look at the trace, have been picked. So have been first thing they have been triggered. So look at this, and they have been picked. So we have in blue and green, P and S white. So next step is to try and locate it. So I'm going to show the dialog where we set this. So we have here locator where we select inversion algorithm. I have chosen in this case simplex combined with Geiger. I'm using a very simple homogeneous velocity model that we can set here, properties for it. And I set here what would be the minimum number of P-wave arrivals that I want to use in the location. I will set it to, let's say, 4. That's a reasonable one. No, I don't expect to have many S waves, so I will set it to 1. Maximum residual. And basically, what we will tell in the algorithm is if we don't have more than at least 4 good arrivals giving us a coherent result, then the location is not reliable, don't locate. Okay. Very quick. Basically, it's failed, and that is because, yep, I set it to have a minimum of 1 good S-wave arrival, and it didn't find a good coherent one in this context. Okay. So I need to relax that criteria. So I'll bring it down. Okay, don't want any. Now locate my events. And now it has located it. This algorithm is pretty fast. But basically, we don't have many stations. And you can see here it's an event on the roof. I'm going to run it now in auto process because they're all being picked. It's located. This is one of the, it's working with a homogeneous model. It's very simple, so it's pretty fast. And I have here the results, and we should have, yeah, we have here our events on the roof, on the floor of our gallery. Okay, so let's go to a more complex data set. For that, it's back to the downhole example that we had before. And in this case, we're going to use our grid search algorithm, collapsing, and we're going to use a layer model. The layer model is defined through a text file. It's outside, and we import it. Okay. So let's have a look at one of the traces, for instance, this one. Let's see how it looks like. Sorry, too many things going on. And we can see here that, yeah, we have some bad peaks, but I'm going to run the location just to show you what. So basically, that's a dialogue with the results of this location. It's iterating, iterative method. So it tries to find the best fit in between observed and theoretical travel time. One of the readings is way off the minimum residual that we have estimated first. Here's the steps. So the first pass is telling me that one of them, in this case, the P wave arrival for the sensor number 7, for the geophone number 7, is an outlier, that it's giving a very high residual compared to the others. So it drops that one. It now iterates with the rest, and now, because it is refining the location, the number 10 is also outside. And it goes on and on and on until it reaches the desired resolution with the minimum residual. And if the number of instruments at the end are still above the minimum that we have requested it to have, we see here we have 6 good arrivals, good P wave arrivals, 12 good S wave arrivals, then it produces a location. And it gives us, well, some source parameters as well, because it does it by default, it does it automatically. And here we see a light blue, and that would be the arrival for the position of the event, of the location. So we can see it's taken into account not all of the readings, of course, not this one, not this one, not this one. They have probably been dropped in the process. But if basically it has taken what would be the median of all of them and the best ones, trying to find a good fit. So it's quite stable against, yeah, mispeaks or difficult readings. And we need to see now if our event is located in a reasonable place. Yeah, probably it is. It is here. That's here. We cannot find it. We can ask it to jump. Let's do a bit of jump stuff. We can see it. We can spot it. Okay. You've seen this process is a bit slower than the one that we did before because it's a layer model and it's got more sensors, triaxial sensors, so it's a bit more involved. Okay, so now we have located our events. What's the next step? Well, we might want to go back and review our processing, because we don't always start with the correct velocity model. We normally start the processing with a homogeneous model, and then we refine our locations. So next step is calibrating our velocity model. And how is it done? Well, if we can, ideally, the best way is, like in this context, this is a lab sample that's being fractured. It's a snapshots of the locations in time. If we can, what we do is perform surveys across our project. Perform surveys every certain fixed time intervals, and see and measure what is the actual, the real velocity propagation at each of these time intervals, and then we get a good estimate or actual measure of the distribution of velocities in our sample. We can input that model in InSite. You can see if we perform a series of surveys across different ray paths in time, we can see how our velocity change. We can track how they change along time, and that's typical because our model, our sample, it's subject to stress. The stress results in changes in transmission velocity. So we cannot use the same model at the beginning as at the end. You can see here at the end, due to fracturing, oops, sorry, come back. Due to fracturing, yeah, the velocities drop significantly. So yeah, we need to take that into account. What happens in the field is not so easy to perform surveys, but we have other tools. We have other bits of information. We normally have in the field some type of shots. There could be surface shots, vibes that we can perform on top, dropping a weight or something like that. We have perforation shots if we are dealing with working with in a hydraulic fracturing job. String shots if we have a downhole well where we can put some loads. Ball drops if we are opening sleeves across horizontal wells. And in the absence of those, we can use an event for which we are pretty sure where it locates, and assume its location and calibrate our velocity model. So InSite have tools to actually calibrate layer models based on as many calibration shots as we have. And it basically what it does is optimize through all of the layers for each of them, the velocity of the P wave, the velocity of the S wave, and the function parameters that characterize anisotropy in each of them. So that is quite a large number of variables to play with. Takes time, but that's why we use the particle swarm optimization to deal with this multi-dimensional search. Yeah, here are all the steps that are in InSite. You can but basically what it does is it changes the velocity. It alters randomly the velocity, P wave, S wave, and anisotropy. Try and locate it, find if it locates, how well does it locate compared with the true location that we know. And if not, run it again until it finds the set of variables that optimize, that give us the best fit. Well, this is a movie showing initial possible solutions, and at the end, all those solutions converge to one. This is it's an example in 2D. It's nothing to do with example of the convergence of this Gaussian optimization. Why we use it? Basically, because it's fast and normally quite stable, quite robust. It will definitely find the best fit. So back to site. Let's have a look at first these time-dependent models that we talked before. So here we have, I'm going to show it in 3D. Here we have a sample cylindrical sample that it's surrounded. It's got a number of sensors, sensors coupled to the surface, to the outer surface of the cylinder, and each of these sensors are capable of switching in between passive and active mode. So that means when they are in active mode, they are sending a pulse across the sample that it's received in all the other sensors. And that's a survey, basically. If we do that across all the different possibilities, we have a very good, almost tomographic imaging of our sample. So we can do that periodically during our test, and we can come up with what would be the velocity model to use in the location for each of the time intervals characterized by these surveys. So what are the tools that we use for this? Basically, we perform surveys. I've got one here. In real time, you will be performing these surveys, so we'll simulate that by importing them into InSite in time and seeing how they come and how they result in different velocities. And if we call the tool called charts, we have many different charts as the name says, to display the different parameters in the processing. But let's show this one first. Basically, we can display here what it's the, in this case, we can choose the parameter to show, the p-wave velocity, calculated through cross correlation, in time, how it changes across a number of ray paths. I've picked 6 of them, in this case. If we go to properties, yeah, I've picked these ray paths. Let's show these ones, just because I know they basically are quite representative of both vertical and horizontal ray paths. We can ask the software to refresh if we are working in real time. So keep looking for information on these ray paths and how velocities are through them. I'll keep it open, okay? And then we can also launch this for information, because we have the perform here. So we can display what's the distribution of velocities across it. We have, yeah, some slow velocities, some ray paths with significant slow velocities, and some with fast velocities, but an average of 3,000 meters per second. Okay. And we can launch, we can call another stereograph to basically display what's the travel time difference. Sorry, I think I didn't click. What's the travel time difference compared with this survey? Because we only have one, and this is the latest one that we have, there's no difference, basically. So I'm going to simulate now that we are working in real time, and we'll be importing surveys into InSite. I'll move it outside so it's not blocking our view. So I'm going to bring more surveys. As we bring a second survey, we can see the chart is updating with more ray paths, and we are seeing some changes. So in fact, initially our velocities are generally increasing. We are compressing our sample. We're probably closing pores or flows in the sample. We perform another survey, still, yeah, yet an increasing velocity. So yeah, we're basically same phenomenon going on there. We perform another survey. Yeah. Let's keep bringing surveys in. So basically, you can see how charts update. Now we're starting to see some damage developing. We have areas where negative changes in velocity are observed. I'm going to import one more. Yeah, and damage is increasing. And finally, this is the last survey. Yeah. Okay. With, yeah, some important damage observed across these ray paths. And that's also, so once we are happy with that, oh, happy we performed that. We can export our velocity model. Yeah, I'm gonna click here, export the time-dependent velocity model, which is basically a text file. I select where I want to save it, and I'm gonna open it just to show how it looks like. And this is how it looks like. It's a text file that basically defines time intervals. And for each time interval, what it automatically does, it looks for what is my fastest ray path. So what's the velocity in that ray path? That is, we don't have as well, so there's no measuring that. It also finds what will be the slowest one, calculates the ratio between them, that's our anisotropy factor, and will give us the direction of the, in this case, of the fastest velocity. Okay, and yeah, for each of the surveys, we have the same observations. You can see generally how even the fast velocity starts to increase, but then it decreases. And yeah, we have quite an important anisotropy developing in our sample. Okay, I'm gonna close this. Let's move on towards the end of this presentation, this webinar, which covers the tools for analyzing our data. And I'm just going to have a quick overview of some of them. There are many more tools for analyze our data, but I will show you the most basic, most important ones. So basically, what's important in our data, it's, I would say, the top information is where our events are locating, what's the damage, what's the volume that they define, but then also it is important the fracturing process and the mechanics, and for that we need to look into source parameters, and we can chart, and there are different ways to source parameters. InSite calculates all of them, and we can give them, we can actually customize the way they are calculated. Oops, sorry, I've gone to the last. And of course, we need to appraise what's the uncertainty in our location. So let's go back to InSite, and here we have an example. I'll go to 3D visualizer. It's a downhole example, the same one that we worked before, with all the events now located. So what's important? What's one of these analyses that we can perform on them? Well, look at what's in our location. And we can do that by, sorry, I click in the wrong place, showing what's the error space used in the inversion. That's what we discussed before. We were looking at the performance of our theoretical array. In this case, it's real. It's giving the residual location algorithm. So, independently, we can define our area of uncertainty. And yeah, we can see here that at least we have a single minimum pretty well defined. And as long as we can call the properties for this, and we can see here the values, what is called here Q factor, in fact, is the residual, the threshold residual. So yeah, we have here a way to characterize what would be the minimum residual or the maximum residual we can have to define well the location of our event. We can probably see that there's probably a higher uncertainty in the vertical, and that's typical because yeah, we're dealing with source vector probably not very well defined. So yeah, travel times are good, they define well, but not so good the vertical resolution. So Okay, this is a way to appraise what's the uncertainty in our location. And yeah, another analysis that we can do, it's calculate. I'm running it now. Apologies for this. Calculate the stimulated volume. And we can do that in many different ways. One is, well, let's show me an ISO surface. That basically fits events, a minimum of events. I define it, I need a minimum of 3 events to define an actual fracture. And if we right click on it, show the properties, it will display what it's, yeah. So yeah, I'm just clicking the wrong place. So yeah, the volume. Other ways to do that, and that's done very often. It's, well, just let me insert an ellipsoid. I can customize that ellipsoid. So I'm gonna edit the properties of it. So for some reason I'm having the back. I have too many dialogues open, so yeah, it's not working correctly. Yeah, anyway, so let's move on to the next one. So other, a more basic way analysis that we can perform. So we have here another data set, just to show the different examples. And here we have, yeah, events, acoustic emission events that have been used. In this case, is a couple of boreholes, very shallow boreholes, 7 meters deep, that are built to mimic what would be the repository boreholes for nuclear waste canisters. So they are subject to some loading. We want to see how the damage zone behaves to being subject to these thermal stresses. And yeah, we can see that there are events induced around them. So just to show visualization aids to interpret our seismicity. So one thing we can do, and I've done that here, but I'll show you how it's done. It's very simple. It's choosing a size and a color scale. So yeah, here we have the dialog for setting up that. We can choose what property, what parameter we want to display as color. Can be wealth of them. Time is quite informative normally. And for size, I've chosen magnitude, in this case location magnitude. And yeah, we can customize the size and the shape of those symbols. Another useful tool is, well, display them in time. Let's replay a movie in time on how our seismic activity develops. So you can see here, it goes from top to bottom normally, but that's because of the stress that we were applying. And then bounces back, and there's more activity going on, moving upwards. So these are some visualization aids that we have to analyze our events. Okay, it's been a long webinar, so we will, in the future, we will have new sessions focused on each of these aspects, but we wanted to have an overview of InSite seismic processing. So, thank you very much for your attention, for joining our webinar today. You can find much more information and examples, case studies, and a free version of InSite for you to evaluate how it works if you visit itasca.co.uk. Drop us an email if you have any questions. If you're an existing user and have any questions, you can always get back to us. If you have this, they don't have to be about InSite, about our generally induced seismicity or seismicity also. And have a look for us in our YouTube channel and our LinkedIn page for examples and news on our products and services. So once again, thank you very much for your attention. Stay safe.